I'm Eric Siegel, CEO and co-founder of Gooder AI. This is the fourth of several short how-to hands-on videos that'll get you started using Gooder AI to evaluate your ML model and plan ML deployment to achieve maximal business value. All the supporting documents you need to follow along and try it yourself are at gooder.ai/hands-on. In the previous video, we reconfigured Gooder. We swapped in this different variation of the savings curve to calculate that monetary value, the savings of the models from the example of targeting payment card fraud detection, based not on a flat value for the true positive gain for the upside of correctly detecting fraud, but one based on incorporating the amount for each case and then a percentage thereof, maybe 85% of the size transaction, because a $5,000 fraudulent transaction costs a lot more than a $100 one, and therefore you save that much more too. So that should be part of the calculation. Great, but we're still talking about and estimating, forecasting the potential monetary value of deploying in terms of the model score. So the way decisions are going to be driven are based on the risk of fraud and only the risk of fraud. Shouldn't the size of the transaction also take into account? That is to say that typically with any predictive AI, predictive analytics project, you get the ML model, it outputs a score, the probability, outcome, behavior predicting for that project, and then you compare it to some fixed threshold. And by the way, that fixed threshold is often sort of set by default by a lot of machine learning software solutions and by a lot of practicing data scientists. It's sort of presumed to be 0.5, 50%. No, it really depends on business factors. Generally, the data, positive and negative cases are imbalanced. You need to take business considerations into account. And in fact, that's one of the main purposes served by Gooder AI, is it allows you to visualize that spectrum of options, and that's what the X coordinate is of most of the charts, is decision boundary, not which corresponds to the decision threshold, but basically, are you going to be treating, are you going to draw that boundary to treat the top 1%, 50%, 70%? It depends, right? So you get to look at those options. But and then that threshold is driving the decision. Let's make a move to not only decide based on that probability, the model's estimated predictive score there that it outputs, but on the actual estimated monetary value of acting on this case. So let's take that score and do something with it before we threshold on it. Let's multiply it by this, in the case of fraud detection, by the size of the transaction. So if it's 30% chance it's fraud, multiplied by the size of the transaction, $100, it's got a $30 expected value. The expected upside of blocking it, the expected downside of not blocking it would be $30. So the expected savings, the upside of blocking it would be $30. And now we're going to be thresholding on a monetary value, not on a probability, not on a risk level, but on a monetary value that's based in part on that risk level, but also on the size of that particular transaction, the expected amount. This is something I don't know if I've seen people talk about. It's not rocket science. It's clearly, so it may be kind of a big paradigm shift because it's so unusual, but it's not a paradigm shift technically or conceptually. It's kind of a no-brainer. So let's look at how that would benefit us in Gooder. Now, within Gooder, we're not actually deploying the model. What we're doing is estimating or forecasting the monetary value of deployment depending on business context, business factors, and where we draw this decision boundary. Right now, from left to right, we're prioritizing, ordering, triaging individual cases based on those risk levels, the model scores, what's the chances that it's fraud. Let's add a new column that's actually the expected value as I just described it. So in the config page here, what I got to with this little gear shift, this little gear logo icon, is you've got this custom columns button. So we're going to create a new column in our test data set that's already been loaded. Call it expected value. And then you can see like some sample code here, but the code thing is really simple. It's actually just sort of augmented JavaScript. But for something simple, it's super straightforward. Just sort of follow this pattern. You have to know the name of the variable. In the data set, the XGBoost1's model scores is called XG1Boost underscore score. And the size of transaction amount. And this is multiplication, of course. I'm multiplying the risk that it's fraud based on what is actually the best of the three models that we saw a second ago by the size of the transaction. So let's add that. And by the way, if you're in there, you need to know the names of the variables. You can go here and see the names of variables, or just obviously look at the test data or whatever. So that's all pretty straightforward. Now, we've added a new column to the data, and it shows here, so I can select it and treat it as a model, right? Models are used to prioritize and triage to order so that then you can draw that decision boundary. So instead of just ordering by model score, let's order by expected value. Now I can select that as a quote-unquote model. It's being used as a model. And then to activate, I actually have to push the plus on the far right here, and now you see that it's been added. So now let's go check it out. You can see, it's up there. Let me just turn it off for a second, just to emphasize. This is what we were looking at a second ago, and now, boom. That is a crazy big deal. We now have a better model at the peak than any of them, right? And that tends to be the case even as we vary these factors that are subject to change and uncertainty. And even better than that, sort of better than that in a way, not only is its peak higher, but it's way farther to the left, and it's pretty flat. So again, if I go to that peak, go to maximum value, I right click, go to maximum value, I've got this flat area. So here I'm standing to save $21.6 million a quarter based on a presumed 10 million transactions per quarter. So over 21 million, and that's gonna, there's, a competing KPI is just how many false positives, how many times are legitimate transactions going to be wrongly blocked, inconveniencing the cardholder. 83,000. That's something that we as a bank would also care about. So let's go way to the left. My expected value is still 20 million, but this went way down to 30,000. So, and in general, just the fact that it's blossomed up here on the far left of curve, that's great news, because typically you're going to only, as a bank, you're going to only want to block, and this is true for so many different kinds of predictive AI projects, you're only going to want to treat, in this case block, a small handful of the individuals, those on the far left, the ones most deserving of that treatment, right? You don't want to block too many transactions in general because of the false positives, and you don't want to disrupt commerce that much, etc. So you can get really high savings way over here, and it makes sense, right? Because now we're standing to gain by also taking into consideration the size of the transaction. That means that if it's a really large transaction, you're going to tend to have a lower tolerance to risk, as well you should, right? So and it makes sense that works out in terms of the bottom line, which is basically the y coordinate here, savings. Because if it's a larger transaction, then the consequences of not blocking it are more dire. And that is to say, the upside of correctly blocking it is a bigger win and bigger addition to the savings. Whereas the other possible error, which is a false positive, inconvenience to the cardholder, if it's a really, really large transaction, the actual amount that you stand to lose with inconveniencing tends to, now it may not be flat, you could put this as a percentage as well, but it would tend to be a much lower percentage. So it tends to not blossom nearly as much. So you have that asymmetry in how the amount affects the true positive, false, the false positive, false negative costs. Although remember that the false negative cost is actually the true positive gain, because by avoiding fraud, we're saving. So right now we're trying to estimate how much we save with fraud detection, right? So that's how the math works out. It's just arithmetic, but it's very particular arithmetic. It's the arithmetic that matters. It's in the context here of a solution, good or AI, that allows you to visualize it, parameterize the business factors subject to change, uncertainty, move them, see how big difference they make. So strictly speaking, the topic of this video of, hey, let's sort of change paradigm and threshold on a monetary expected savings or expected value rather than simply a probability or risk level. That's not a gooder thing. You can do that. It's just that gooder is very conducive to take a look at that. So now typically the transaction side would be taken into account at a bank with business rules, if-then rules, basically. So it would put these transactions into a few groups, and the really large transactions would have a lower tolerance to risk, and the smaller transactions would have a higher tolerance to risk. But that's clunky and is clearly going to be suboptimal compared to doing it in this continuous way, right? Which is straightforward. It goes straight on the bottom line. You see it. So let me show you two more examples, because we're seeing this have a great potential benefit across all different kinds of use cases of predictive AI, of enterprise machine learning. Here we are, sort of similar, is return check prevention. This is based on data from a large online retailer. So checks be like ACH transactions, which can bounce either because it's fraudulent or because of lack of fund. Either way, you're going to lose out as the retailer. So let's add expected value to make that decision. Look, we've got all these great options now, even without disrupting commerce, without turning away nearly as many transactions over here on the far left. Non-profit fundraising. In this case, it's not the transaction amount. It's not the amount that they donated, because you don't know that till after. You can't use that in the prediction, right? You can't use that in driving decision of whether to expend the cost of contact or treatment or the wining and dining by a charity officer or what have you. But boom, what you do have is how deep their pockets are, an estimation of their wealth, right? Known here as the estimated capacity of the donor. Once again, makes a huge difference if you're prioritizing the investment of some kind of treatment of an expense on a prospective donor based in part on that as well, again, based on expected value. We've also seen it for churn modeling, collections, and credit scoring, like deciding whether to approve a loan application. It doesn't apply to every predictive AI project, but take a moment to think about it. There's lots of predictive AI projects where you can stand to benefit so greatly by taking this really minor step of transitioning from just pure model score probability, risk levels, whatever you want to call it, to a monetary the estimated value, the estimated savings, the estimated gain in monetary terms, and driving decisions in that way. So we're doing sort of two monetary things here that aren't usually done. One is estimating the potential value, forecasting the value of the model in its deployment in monetary terms. And we're also looking at driving that deployment so that it drives decisions based on those monetary terms. So estimated value, multiply probability times amount.